knowledge levels. If you need some homework help or tutoring, check out the links in the description below. And with that, let's begin with these set of questions. So with that, let's hop right to it. So hopefully you can see my screen. Just double check that. Okay, well, let's begin. And now the first question, we're talking about classifying each compound as ionic, molecular, and they're giving us 4 of them, okay? So is it ionic or molecular? And we're given CO2, that's carbon dioxide, NiCl, that's nickel chloride, NaI, that's sodium iodide, and PCl3, not PC13, PCl3, and that's phosphorus trichloride. So with that, let's break down what does it mean to be ionic and what does it mean to be molecular. So ionic molecules, they are when 2 elements, a metallic element and a non-metallic element, are bonded together. When those 2 bond, those form an ionic bond. So metal bonded with non-metal, and this bond right here is ionic bond. And now with a molecular compound, it's when it's a non-metal and non-metal bonded together, and that right there is a covalent bond. Okay, so that's how it breaks down, and now I want you to classify them. So we're going to use this space down here, just going to highlight it so we know where we're going to write it as where we're going to put the classification. Okay, so with that, let's break it down. Easiest way to go about these type of questions is just refer to your periodic table, which you are free to use. Some classes just want you to memorize the basic ones, but for ease and for familiarity, we're going to be using the periodic table just to be able to get these few ones in. Okay, so let's start with CO2, carbon dioxide. So carbon molecule is listed as a non-metal, so we're going to label, so let's make it non-metals will be green, so that's non-metal, and metals will be red. So with that logic, C, non-metal, circle it in green. Oxygen, also non-metal, green. So 2 greens, 2 non-metals. So with that, this is a covalent bond. Okay, now let's move on. Nickel is a transition metal, which still counts as a metal. So with that, circle it in red, metal. Chlorine, you see here, it's a halogen, another non-metal. Okay, so now we have a metal and non-metal. So with that, this is an ionic compound. Okay, sodium iodide. Sodium is an alkali metal, again metal. Iodine is a non-metal. As you can see, it's another halogen. So with that, this is going to be an ionic bond because it's a metal and a non-metal. And now for the last one, phosphorus trichloride. Now with this, phosphorus still considered a non-metal, so let's circle that in green. And chlorine, still non-metal, even based on what we did from the previous part. So with that, this is also a covalent bond. Oops, let me just write that better. Covalent. Now with that, we have covalent, ionic, ionic, covalent. Now this is just for extra information, but as you notice when I was calling out their names, you notice that these 2, this is nickel chloride and sodium iodide, but these covalent ones, they're called carbon dioxide and phosphorus trichloride. You'll see when it comes to covalent bonds, they usually like to reflect whether there's multiple of them in their name. Because for example, I could also say, let's say calcium iodide, since calcium prefers 2 of them, it would be CaI2, and it'll still be called calcium iodide and not calcium diiodide, for example. And this would also be an ionic. It's just something to know for future reference if they start giving you the names instead of the formula and tell you to classify it still. So with that, let's check if they have it correct here. So the answer A is molecular. Yep. So that's covalent molecular. And these two, ionic, ionic. And then the last one is covalent compound. So there we go. So just to clarify, these are molecular. I just named the bonds in them. But once you have a covalent bond, it makes it a molecular compound. Okay? So that is correct here. And just reading through it, it explains that carbon is non-metal, which is what I said. Nickel is a metal. And also sodium is also a metal. And the rest of these, as you can see, are non-metals. And depending on which is bonded with, it makes an ionic or molecular compound. Okay, so with that, we got our first question correct. And let's move on to the next one. Okay, so with that, let's now go into balancing the following equation. So, okay, we have to balance the equation, but it's very important in basic conditions. And phases are optional. But what does it mean to be in basic conditions? And that means, okay, in this case specifically, there's a surplus of hydroxide ions, OH minus. That is what it means. So this is a thing you're going to be probably throwing into the equation if you need to balance some things out. Now, with this, we're going to break down step by step what we should do to answer a behemoth of a question like this, because it can get quite complicated. And if you do try to just balance it out based on what you see, you'll most likely end up lost because you don't really know where to go from there. So with that, let's write it out. So CO, so cobalt chloride. This is an example of an ionic compound, by the way, plus sodium oxide. It probably has a different name though, because this is a different one. You notice it's Na2O2. Usually you would see Na2O. So this one's already very strange. And this turns into cobalt hydroxide, COH3, like that, plus Cl, that's chlorine, and sodium. And they're just kind of floating there as ions, okay? So this is what we have as our starting equation. Now, I'm going to break this down by steps because it's very important that we do this the right way. At first glance, you're probably just going to see like, oh, I need to balance out the chlorine or the sodium. Those ones can wait. The first thing we need to do here, okay, as number one, first step, is to write down oxidation number. Okay, so an oxidation number is a number given to the element in question based on what charge it should have. And there's a list of certain things that come with an automatic oxidation number, meaning that the other one is bonded to has to adjust for it. Perfect example, based on the one we're starting with actually, chlorine in cobalt chloride wants to be -1 because that's just its natural state. Okay, and that's the one we refer to because it's the halogen. It's one of the stronger stronger reduction agents. You will notice that if we actually go to the periodic table, when it goes from bottom left to top right, so all the way, it's kind of like an arrow that points upward this way, the stronger its electronegativity, and that means fluorine up there is like the strongest reduction, oxidizing agent, because it likes to be reduced. It likes to take an electron. Okay, but that's just extra information. But the point being overall is that chlorine really likes to be that -1, but there's two of them, meaning that cobalt has to make up for it. Okay, so that means it needs, for it to have this charge in total to be a net charge of 0, this has to be a -2. I mean a +2, sorry. And with that, it means that cobalt's whole thing, since there's only one of them, is +2. So now we know the oxidation numbers for these elements here. And we do the rest for this one. Now sodium is actually on the opposite spectrum. That's one we use. So because it's not a transition metal like cobalt, it kind of has a set state. Because it's an alkali metal, it always likes to be +1. Okay, and there's 2 of them, so that means plus 2, and that means oxygen has to make up for it by being minus 2, and that means this oxygen here is minus 1. Normally, as you'll see later, oxygen likes to be minus 2, but there are a few exceptions, such as that one. Okay, now let's move on to this cobalt hydroxide. Okay, we start with the hydrogen. That one, except for very rare scenarios, it always likes to be plus 1. Okay, so right above it, right above his little head, plus 1. And oxygen, like I said, especially when bonded to hydrogen, likes to keep its minus 2. Okay, so with that we have a minus 2 plus 1. In total, this is going to be negative 1, but there's 3 of them, so in total this is negative 3. That means this cobalt, unlike the previous one, instead of it being plus 2, it's now plus 3. Okay, so that's what we're dealing with there. And now, with that, we now move on to the chlorine. It just has a minus there, so this is just going to be minus 1. Sodium just has a plus, so this is just going to be plus 1. So we successfully written down the oxidation numbers for everything. And now what we want to do is see what's changed, okay? So we notice that this went from a plus 2 to a plus 3, and oxygen went from a minus 1 to a minus 2 right there, okay? And these are the equations we balance first, because that way we don't get lost. So the new equations, well, just a half equations would be, so cobalt 2 plus, 'cause that's what it was, turns into cobalt 3 plus. Now how is this possible? Only way this can happen is if cobalt loses an electron. When you lose an electron, you become more positive, meaning that on the product side there's going to be an extra electron just, you know, relaxing, chilling, not doing much. So now we have to write down the oxygen one. So oxygen goes from minus 1 turns into oxygen 2 minus. Okay, whoops, let me keep it consistent. 1 minus. You usually don't see that, you just see a negative, so let's keep it like that, keep it consistent. So now for it to get more negative, it needs to gain an electron, so you need to write the electron in the positive, in the products, in the reactant side. So in the reactant side, you see an electron plus oxygen makes that. And now you go back to the equation, you see that there was 2 of these oxygens, so that means you have to just put a 2 in front of it, and it'll make 2 of these in the products. At least that's what it should do in the products end. We won't fix this side, we're just seeing what's happening initially, okay? But the only way for this to happen, for it to now change 2 oxygens, you need 2 electrons. And because now you want to balance these 2 out, these are the 2 equations you're balancing. You notice that there's 2 electrons going to the products, but only 1 coming out. Into the reactants, but only 1 coming out of the products. So you need to double this equation here in order to make up for it. So in actuality, you have 2, 2, and 2. And now the 2 electrons from the product side will cancel out with the 2 electrons from the reactant side. And this right here is the equation you're going to be working with to balance out the rest of it, okay? So that was step number 2, okay? Just to write it down, balance equation based on electrons and change in oxidation number. Okay, and now let's go to step 3. What you want to do, step 3, is kind of just fill in. Now that we have this stuff, we use that to fill into the equation what we started out with. So now that we know that there's 2 cobalts involved, instead of it being COCl2, we'll have 2 COCl2 plus Na2O2. This one doesn't change because we already said there was 2 oxygens, and that turns into 2 got so used to the first one, COOH3 plus Cl minus plus Na plus. So that's what we have right now. But quickly we can make some changes as we're filling it in, because we see 2 COCl2. That means there's 4 chlorines in total that are working. This one only has 1. We need to multiply this by 4. Na2O2, same thing, only 2 sodiums, so we need 2 more. I mean only 1 sodium, so we need to double it. That's what we have right now. Now, at step 4, you notice that, hold up, wait a minute, there is now a net charge on this side of -2. But this net is 0. How do we fix that? Well, finally, that's where the hydroxide plays in, because it's in basic conditions, and when you have basic conditions, you have free roaming hydroxides, OH minus, and that's key because that minus is what's going to use in the reactant side to balance out the net charge. Okay, so fixed charges with OH minus. So now we're going to get OHs fill in. Now how many do we need? To make it a net charge of -2 like this side, we need to then add 2 OHs. So now as our equation, we're going to have 2 OH minus, now we fix a charge, 2 COCl2 plus Na2O2 turns into 2 COOH3 plus 4Cl minus plus 2Na plus. As you can see, it's getting quite lengthy. So now we've done that. Okay, so our last component here is, first we got to check through and make sure everything's balanced. So as I'm going through though, the only difference right off the bat, or actually 2 differences, but the main one is that we have 6 hydrogens here. Okay, because 2 times 3, 6 hydrogens, and we only have 2 hydrogens here. The next thing I notice here is that when I'm going through all of it, there's 2 oxygens and then 2 more back here, so we have a total of 4 oxygens. Okay, but here we have 2 times 3, we have 6 oxygens. So how are we going to make up for the difference here? Luckily, something that conveniently adds the 4 hydrogens missing and the 2 oxygens missing is water. How many specifically? 2 of them, because 2H2O. And this right here is our last component in redox reactions. Okay, because it depends on which conditions they specify, but usually whenever you're now missing components, specifically only hydrogen and oxygen, you see how you can fill it in with water, but that only works after you've gone through each and every one of these previous steps. So number 5, that's going to be more like add water if need be. That's step 5. And we see here, only place we need to add water is in the reactants. And the reason why it wasn't added before, as you can see when you balance equations, sometimes water isn't really used in the reaction. In this specific case, in this redox reaction, it is. So now that we've added water, our full formula is going to now be 2COCl2, so the original, plus Na2O2, plus the hydronium ions we discussed earlier, plus water, and that turns into 2COOH3 plus 4Cl minus plus 2Na plus. Barely fit there. Whew, close one. And now with that last check, we're just going to see if everything is properly balanced. And while we're checking if it's balanced, we're actually going to compare with their answer here. So we have 2 cobalts. So let me just highlight it to keep track. 2 cobalts, 2 cobalts, 4 chlorines, 2 sodiums, 2, 4, 6 oxygens, 2 plus 4, so 6 hydrogens and 6 hydrogens. And now the charge we have from this -2 net charge, and from this -2 net charge. This is now fully balanced. Okay, and now let's see what they got here. So interesting enough, they did it a little bit of a different way. They're saying that you should balance the half reactions. The only issue I have with it is that you notice that we go from cobalt chloride to now cobalt hydroxide plus chloride. We don't really see where the hydroxide came from, and then when they go through the question, you end up with the hydroxides, but you kind of wonder how they did it. So when they say just balance the half reactions, it can get a little bit tricky there. It does depend on whether or not they provide these half reactions fully in terms of like the list of different half reactions when you go through the electronegativity. But if they don't, that's why you first should start with writing down the oxidation number. That way you know exactly what's changing. Because kind of just going at glance at eye's view, you might get lost in it. So let's just skip then to the end, because they just say to balance the first half reaction and the second one. But let's just see how if they got at least the right answer. So when we compare 2ClOCl2 plus 2OH minus plus Na2O2 plus 2H2O, perfect. It goes to 2COOH3 plus 4Cl minus plus 2Na plus. Awesome. So they at least got the right answer, but I would definitely go with this technique here. So oxidation number, balance the equation based on that oxidation number change and the electrons that are moved. You fill it in, and then you fix the charge difference with OH minus, and then you add water if need be. Okay, so let me just leave a quick comment. Correct, but start with oxidation numbers and balance from the change in oxidation numbers. Okay, so that's what we have there for question 2, and now let's move on to question 3 for today at least. So with that, the third question is talking about the Ka of Chloros Acid. So that's HClO2. So Ka, let's make this all black for now so we can keep track. So the Ka of HClO2, that's Chloros acid, is 1.1 times 10 to the negative 2. Okay, Ka means pretty much like how much you disassociated. So if you have a solution and you throw in hydrochloric acid, not hydrochloric acid, HCl, of Chloros acid, so HClO2, what happens there is that this is how much of that HClO2 breaks down into its components. And I will show those components by writing out the full equation. Okay, so HClO2, when thrown into water, you just usually don't see the water part, but this is important for this specific scenario. In fact, for this scenario, it's actually important to include their states. So this is aqueous, and water is just going to be liquid. Very important distinction. And that turns into ClO2 minus aqueous plus H3O, and that's a hydronium ion, which is usually what they use to actually calculate acidity. Aqueous. Okay, so this is the formula we're working with, and the Ka is that. So this means that when you throw in HClO2 here, it means that overall, when it shows that to a negative 2, it's not going to produce that much of these components. It's going to be like maybe like 1/100th of it according to this, because 10 to the negative 2 is 1 over 100. So like not much of these two come out of it. And that right there, when they give us that Ka, it's important to say that this is going to be, in big letters, a weak acid. That helps us answer this question, okay? Because as you'll see later, and even how they solve this question, that distinction is important. So what they're asking for here is, what is the pH of, if you use 0.35 as the initial thing? So if we had 0.35 moles per liter, so of HClO2, what is the pH going to be of that? And so what we do to solve this, okay, is that because it's a weak acid, we need an ICE table. An ICE table stands for initial, change, and equilibrium, okay? And we only include the components that are aqueous, no solids and no liquids. So that means 3 of these 4 make it to the next round. It's going to be HClO2 and ClO2 minus and H3O plus. Now it's important that we distinguish between reactants and products, okay? Because that's going to be very important how we break this down. So we initially started with 0.35 moles per liter, okay? And then these ones are 0. It doesn't say we threw in like a salt or anything. It just says we have 0.35 moles and we want to see how much it dissociates. That's what we're solving for. So because it was thrown into water, okay, it's going to dissociate, meaning we're going to lose some of the Chloros acid, okay? So we're going to have minus X here. We just don't know how much. We're now going to lose some. And this is going to be plus X and plus X, okay? Now, as a tidbit here, if this was a strong acid, you wouldn't even bother doing this, because strong acids, their Ka goes at least above 1. They're like 13, it could be like 100 and something. Very strong acids have very high Ka. That pretty much means this: if you start with 0.35 moles in a strong acid, everything would get turned into hydronium and its component, okay? So here, in this case, because it's a weak acid, that's not the case. That's just for future reference. So it would have been a lot easier to solve if this was a strong acid, because of the fact that if you start out with 0.35 moles of the strong acid, you would definitely have 0.35 moles of the hydronium produced. All right. Now back to this question specifically. Here, what we want to do to make it easier for us overall is we want to distinguish. The reason why we break it down like this is because HClO2 is what you consider the HA, which what we call the acid. And here, the ClO2 minus is A minus, which is called the conjugate base. So HA is a conjugate acid, A minus is a conjugate base, and this is just, you know, the hydronium. So that's going to play into our equation here in terms of how we even solve for Ka, because that's what we're going to use to find out what X is. Now, let's continue on. So our equilibrium is now going to be 0.35 minus X. And our ClO2 minus and H3O plus are just going to be X's, okay? Now, here's a formula we use to find Ka based on the conjugate acid and its conjugate base. So Ka is equal to, all right, the moles per liter of the conjugate base, A minus, times the moles per liter of hydronium in there, over the moles per liter of the conjugate acid, HA. So this is the formula we're going to use to find X, because right now we're given Ka, so that was a check, and we're given pieces of these but not the whole thing. So if we write Ka, it's 1.1 times 10 to the negative 2, so really it's just 0.011. That's what it is, and that's equal to A minus. We just know it's going to be an X, and H3O plus also an X, so you can just say that's going to be X squared. And HA is actually 0.35 minus X. Now here's a little cool thing. This would have been super easier to solve if, like, you see how it's just X squared? If X was so small that that 0.35 wouldn't change much, then we could have just done like the square root of like 0.11 times 0.35. That would have been it. But because, as you can see here, the Ka is actually quite big, so the rule of thumb that they usually use is that if the Ka is greater than 1/1000th of the starting amount, like the moles per liter, then you can't ignore it. This X has to be included into the equation, so you can't just throw it away and say, oh. But if it is smaller than that, so for example, if the Ka was like 10 to the negative 8, we wouldn't need to use this X, because you can see right then and there that not much of the base, of its conjugate base, would be produced. So it would be like negligible. So with that though, because it, as you can see, is a pretty large Ka, I'd say like this makes up for like maybe a little bit more than 1/100th, like around there. But yeah, so that's just a good thing to know because it could save you some time, but unfortunately in this one we can't take the shortcut. So now let's solve for it, because now because of that we're going to need to use a quadratic formula. So you know the whole b, negative b plus or minus, you know, b squared minus 4ac over 2a. This is what we're going to need. Reason being is because as you solve for this, you'll notice that it'll be 0.011 times 0.35 minus 0.011 x is equal to x squared. And now if we move everything to the right so that way it can equal 0, it's going to be x squared plus 0.011 x minus whatever these two multiply into is equal to 0. And that's when we use our quadratic formula, because a is going to be, so it's a, I'm going to write under it, so a is equal to 1 here, and b, because it's going to be the number multiplied to the x, so that one's going to be 0.011, and c is going to be just whatever this behemoth is. It's going to be 0.011 times 0.35. So that's a, b, and c. So now we just plug it into our quadratic equation. So it's going to be negative 0.011 plus or minus the square root of 0.011 squared minus, but instead of a minus, you notice that because c is a negative number, whoops, I didn't even include that. So c is equal to negative, okay, of that, because, you know, it's being subtracted. Because the negative number, if you're subtracting negative, it means you're going to be adding it. So it's going to be plus 4 times 1 times 0.011 times 0.35. That's what we're going to have there. All of this over 2, because a is still 1. And as you solve for it, okay, if you plug in all these numbers correctly in your calculator, you'll get 2 answers. Because of the plus and minus here, that's very important. Okay, you get 2 answers. You get 0.057 as 1 and negative 0.068. Now you notice right away there could only be one possibility, because you cannot get a negative amount of product. That's just not possible. You cannot get more reactant and get less than 0 product. So with that, we can just cross this option out. We don't need that. Okay, so this is going to be our x. This is how much product is made. So this is how much, not only of the ClO2 minus, the conjugate base, but also the H3O plus. So H3O plus, that is going to be 0.057 moles per liter. Okay, so now that we know that, okay, we can now use this to solve for the pH, which was the original question. Can you imagine that, having to do all this just to find out the pH? So with that known, because this is the only component we need, we don't use a conjugate base, we only use hydronium for pH, because the formula is pH is equal to negative log of that concentration, 0.0, well, let me write it properly so you can have this formula for later, negative log of H3O plus, okay, which is now, as you see, negative log of 0.057 moles per liter. That's the concentration. So when you plug it into your calculator properly, you'll get that the pH of this question is equal to 1.24. That's the pH you should get. Let me just write this better so you can see it. 1.24. All right. So with that, let's just break it down. Because we discovered it was a weak acid due to its Ka being less than 1. Okay, strong acids usually have a number greater than 1. All right. because of that, we can say it's a weak acid. And because of weak acid, we need to use an ice table, okay? And because we use an ice table, we're able to find out how much hydronium was actually produced, okay, which is this much. And because of that, we just use this pH formula to find out that the pH is 1.24. So let's see here what they did. So with this, why I kept emphasizing weak acid is, as you can see here, they say the value tells that this is a strong acid, which is incorrect. That is 10 to the negative 2. This is a weak acid, not a strong acid. Okay, so the solution will not have all of the acid associated. So they skipped ahead and just assumed that it was a strong acid, and that's how they got just the negative log of 0.35, because you can see that's what we started off with, quote unquote. So with that though, that one is incorrect. This is how you actually solve it. So this is a weak acid, so you have to use an ice table. Whoops. To use an ice table and solve for the concentration of hydronium. Okay, so that's it for that question. Just make sure that you notice if it's weak or strong acids. Remember, greater than 1, strong acid; less than 1, which this one is, weak acid. That's usually the rule of thumb. It might change here and there based on who your instructor is or what they're using as a reference in terms of their textbooks, but that's usually the rule of thumb. All right, so now let's see this question here. So question, it says, now let me just start from the top. So at 477 Kelvin, okay, and 645 millimeters of mercury, that's just a way to read atmospheric pressure. What volume, so how much N2 volume reacts completely with H2? How much of it? 29.2 liters, okay, to produce NH3. So the first thing we do here for this equation, we solve the formula. We have N2 plus H2 turns into NH3. So first thing we do is just try to balance it out. So you see here we have 2 nitrogens but only 1 in the products, so we need 2 nitrogens in the products. So now in the reactants though, we only have 2 hydrogens and 6 hydrogens in the products, so we need to multiply that by 3. This right here is a balanced equation. We're going to refer to converting our moles. Now we would need to go through all the steps of using this formula for per se, PV equals nRT, but this is one of those questions that's an exception of using this equation, because you notice they said at 477 Kelvin and 645 millimeters of mercury. They did not say this changed. This question is constant temperature and pressure. So using that, and with following the laws of mass change and everything, matter cannot be created or destroyed, it can only be changed and everything else. This allows us to just be able to convert straight from the moles to the volume, because of the fact that the temperature and the pressure stays the same. You don't need to convert the volume of hydrogen into the moles of hydrogen, and then the moles of hydrogen into the moles of nitrogen, and the moles of nitrogen back to the volume. You can literally just go into the ratio. So the normal steps, usually you would go volume of hydrogen, you'd use the PV nRT, so this formula here, you solve for the moles, so then you get the moles of hydrogen, and then use this formula up here to now solve for the moles of nitrogen, and then you'd convert it back using the PV and RT to volume of nitrogen. Now this steps here only applies when the pressure and temperature change in the process. But if those two stay the same, then that means the volume is now simply just a 1-to-1, or in this case 1-to-3 ratio. Okay, so here what I did to solve it is that the amount of volume, well actually these are right moles on top, the amount of moles per the amount of volume of nitrogen has to equal the amount of moles per the amount of volume of hydrogen. Okay, this is how I solved it, a much quicker way, only because the pressure and temperature were constant. Okay, so with that, we do not actually, we know the ratio of moles to hydrogen, so this is going to be 1. Okay, it's equal to, and we know the hydrogen is 3, that, and also 29.2, that's the volume of hydrogen. And here, what's the volume of nitrogen? We don't know. This is our x, and we just solve for x. So then we end up with x is equal to 29.2 over 3. So that means the moles of hydrogen, well not moles, the volume of nitrogen, okay, it's just going to be equal to 9.73. And if you round it up, the only option that works is D. So the answer for this question is D. And the only reason why we're able to use a shortcut is, like I said, constant temperature and pressure. If not, please follow this way using the PV equals nRT equations on this step here when you convert from volume to moles, and this step here when you convert from moles back to volume, okay? If the temperature and pressure are changing. If you're not sure about this changing things, or in terms of any of the constants that might be changing, just use the PV equals nRT so you can get the right answer. As you see here, that's what they did. They used PV equals nRT, and they were able to now, you know, break it down. They first went from the volume to the moles of hydrogen, and they found 0.633, and then they used that to find how much nitrogen, divide that by 3, so 0.211, and then they used PV and nRT again to get it back to the volume, and they do end up getting 9.73. So same answer, just different ways of working it. Just make sure you pay attention to what's given to you, okay? All right, so with that, let's move on to the next question. Okay, so this question here is just asking, of these 4 components, which is the most acidic? So which is most acidic? So with that, let's find out which ones they're talking about. Okay, we have this thing, so double bonded oxygen just right there, and then we have this thing, double bond oxygen but with an OH pair right there. We have this, which is very similar, but this is missing an O minus. Okay, this way of tracking it. And then as last one we have an NH2. So let's break it down by which is most acidic. So let's start with which ones can actually give away hydrogens. Alright, so with that being our first indicator, this one's out, because carbons usually aren't the ones to be given hydrogens. You want to be able to see like an oxygen trying to give away a hydrogen. Alright, so that one won't work. And with that logic, this one also won't work because it has no hydrogen to give. Carbons bonded to hydrogens, those ones don't count as hydrogen bonds, which is what you're looking for. You want, because things that are hydrogen bonds, those are the ones that are bonded to like oxygen, nitrogen. Okay, those two are the hydrogen bonds that you're looking for in these cases most of the time. So with that, this one, oh look, it has hydrogens, and this one also has hydrogen. So these ones are contenders currently. Now, before we hop straight to the answer though, NH2, this actually works differently in terms of its hydrogen bonds and everything, because what it prefers to do, instead of giving away a hydrogen, it likes to do what I call, taking one. So what it prefers to go to is NH3 plus. I'm sure you've heard of it. So this right here is ammonium, okay? And that's what it likes to do right there. So NH3 plus is going to be what it likes to do over there. All right, and because it likes to take a hydrogen instead of giving it away, that would actually make this a base. This will be basic. All right, so this is no longer a contender. Now this oxygen, what it likes to do, funny enough, they actually gave you the answer next to it, because this is the form it would take. It would give away this hydrogen here and just be an O minus. Now you're probably wondering, okay, but why would it give it the oxygen? I mean, why would the oxygen give the hydrogen? And why in this scenario, let's say if we had this is one of them, why would this one work? Because this is actually an alcohol. This one wouldn't work because there's no resonance structure. This oxygen is in a really awkward position to give away a hydrogen. It doesn't just want to be negative, it wants to be in a balanced state. When you give away that hydrogen while you have this oxygen, you end up with a structure like that, where these two oxygen just kind of sharing that double bond. And this resonance structure is what makes those type of molecules be able to do what it can do. And that's why that's the most acidic. Now, fun note is that if you actually got comfortable with the nomenclature, you'd notice what to call these. So this is a double bond here with two functional groups on the left and the right. So this right here is a ketone. All right. This, funny enough, is actually called a carboxylic acid. And so right off the bat in its name, you know, this is going to be the most acidic, most likely. This right here is this thing's conjugate base, as we discussed earlier. So if this was HA, let me just write it a different color. I'm trying to think. No, actually, blue works. If this was HA right here, this carboxylic acid, this would be its A minus. That's pretty much what it is. And that means it wouldn't work because it's already done its job of giving away the hydrogen. And now as the last thing, this right here is an amide. And most of the amides are basic. So if you kind of were familiar with nomenclature and you could actually recognize them based on their formula, you could actually then also figure out which is the most acidic. So now let's see what they have here in terms of the answer. So this one, as they also mentioned, the first one, the ketone, as we discussed, it's not able to give away any of its hydrogens because it's bonded to carbons. Those don't count as hydrogen bonds. Now they mentioned the OH, it's able to give away its hydrogen. This is going to be probably the most acidic. Now this one, the conjugate base, is, you know, already done its job, can't do it again, so it's not going to be acidic anymore. And NH2, it's actually basic, so as we discussed, it wants to turn to NH3 plus. Okay, so with that logic, as they said, which is correct, 2 is the correct answer. So let's continue. All right, so now with that, let's hop right into the next question. Okay, so we have here, determine whether the following pairs of elements can form ionic compounds. So this one is kind of, we've literally already gone through this already, as long as you're paying attention to the earlier part of the video. If you're interested in only answering this question, for example, though, we know as review, ionic compound is when it's a metallic, so metal, and non-metal bonded together. Molecular compound are non-metal and non-metal, and that right there is a covalent bond, and this is ionic bond. And one that we don't really discuss as the last type, which is more rare or just not as explored in most chemistry teachings, is metallic compounds, which, if you guessed it, is just metal and metal, and that's a metallic bond. So ionic, covalent, and metallic bond. This is just how I write it. They obviously look quite different when you actually try to show like its valence structure and everything, but this is just the basis of what we go by. So now with this question, we then again refer back to our periodic table to make it easier. But first, let's write down what we're dealing with. So we have oxygen and calcium, sulfur and bromide. Oops, sulfur just an S. And bromide, lithium, Li, and fluorine. Lithium again, and calcium. Nickel and chlorine. And the last one, chlorine and sodium. So now let's go to our periodic table. So oxygen and calcium. Calcium is an alkali metal. If you remember, we just do the same color coordination. Metal, and this is a non-metal. So oxygen, non-metal. In fact, let's just go through. Calcium, metal. Sulfur, let's see here, is a non-metal. Bromine, also a non-metal. Lithium is a metal. Fluorine is a non-metal. Whoops, different colors, haha. Fluorine is a non-metal. Chlorine is a non-metal. Really gotta fix those colors. And sodium is a metal. Okay, nickel is a transition metal, which still counts as a metal. And chlorine, again, we've seen it before, non-metal. Lithium and calcium, we've seen lithium, we've seen calcium, so these are both metals. So now that we've labeled all of them, let's see which ones we can actually box in as an ionic compound. This one, fulfills the requirements. So does this one. So does this one. And funny enough, NaCl, that is actually just salt. And so does this one. So 4 of these 6 fill in the requirements of a metal and a non-metal bonded, which means that those 4 are ionic compounds. Now let's see if we're correct. So calcium and oxygen, they do say it's ionic. Sulfur and bromine, it's just a molecular compound, which is non-ionic. Lithium and fluorine, ionic. Chlorine and sodium, ionic, perfect. Nickel and chlorine, also ionic. And lithium and calcium, both are metals. This will be that metallic compound. Okay? And with that, they're correct. So let me, okay, that's weird. Thank you. So with that, hopefully we've had a good review on what are ionic and molecular compounds. So now for the next piece. So with that being said, let's go on to the next section here, just to double check. All right, so we have 2 structures here, papyridine and aniline. So papyridine is a 6-ring structure, and I would call it a carbon ring, but the only thing is that the nitrogen is just snuck right in there, so I can only say 6-ring structure. And as the last piece, it's a hydrogen. Okay, that's papyridine. My picture may not be as nice as that one, but it does its job, hopefully. And aniline is now an aromatic because it has a benzene ring. So that's what that is. As you notice, whenever you see something like that and you don't see any nitrogens in it, it's just carbons, double bond, double bond, double bond, like 3 of them specifically. That's what you call benzene ring. Okay, so the benzene ring attached to, as we discussed earlier, amide, NH2. Okay, so that's aniline. Now if we to draw the same way that we draw papyridine, this is what aniline looks like. Okay, so with that, they're asking us to now draw N-methylpapyridine. So we have now, instead of papyridine, we have methyl, Papyridine, and we have N dimethyl Papyridine. Okay. Whoops, no, dimethyl aniline. So right off the bat, okay, you know that because these two have the same ending and these two have the same ending, is that these two structures are going to be very similar to each other. We just now notice a difference. So with this, when you go back to your nomenclature, you know that when they say methyl, or when they have a prefix, of something indicating like methyl, ethyl, propyl, it means that there is going to be a chain, and the thing before that prefix, the N, for example, tells us where it's located. So because it says N, we know it's going to be on the nitrogen, meaning that the nitrogen gets rid of a hydrogen and gets replaced by what's it called? I'm losing the word for it, but a functional group. There we go. It get replaced by a functional group. So methyl, this is a quick review. Methyl looks like a functional group and just a line because it's just carbon. Ethyl looks like that and two lines because it's two bonds. Let me just make it more clear. And propyl, R3, and you kind of get the gist. It can keep going past this, butyl, pentyl, and it keeps going on and on, but pretty much this is what it looks like. So now we have where it is, we have the length of it, and we know what the original structure looks like. So with that, we can actually draw what this would look like. So this is going to be a 6 carbon ring. Got to get my house tops better. Well, I call it 6 carbon, which is not it. It's just a 6 ring because nitrogen is there. And instead of this hydrogen gets kicked out. So unfortunately, he no longer makes the cut and is replaced by just like that. So it looks very similar to the picture, but now instead of actually distinguishing, saying it's an H, you just draw that line, because this line right here, this signifies that there's a CH3 bonded to it. So carbon initially bonded to the nitrogen, followed by it splitting into 3 hydrogens that is bonded to fulfill that 4 structure. And now let's go into NN dimethyl aniline. You see dimethyl, as in DI, not di. But point being is that because it's a dimethyl, that means 2. So that means you have 2 methyls attached to that N in the aniline, hence why it has NN. It tells you both of them are attached to the N. And the reason why this is good, because you notice right off the bat, this nitrogen had 2 hydrogens. So now both of these hydrogens don't make the cut anymore. So now what you have is your picture is you have the benzene ring, okay, and now the nitrogen, and they just have 2 little sticks sticking out, because that signifies, oh, we no longer have the hydrogens, we now have CH3s in each part. Okay, so that's how you draw them. But this is now asking you to classify each of these as a primary, secondary, or tertiary amine. So primary means that nitrogen has only bonded with 1 carbon. So it looks like this. So primary would look like N, actually as a picture, just to make it easier, it looks like this. A functional group, 2N, because that's what, carbon, and then just 2 H's. And a functional group, are going to be that carbon chain, okay? And then secondary would be, same thing, but instead of it doing, just give it some more space actually. Secondary, it'd be like the functional group and another functional group and then H, okay? And tertiary, you probably guessed it, it's going to be N just surrounded by these functional groups. And that's all nitrogen can do, because if you notice with nitrogen, it's the 5th, it's on like the quote unquote 5th row, but point being is that it wants to have full shell, but it already has 5 electrons. So that's why it can only take 3, because you notice that there's always going to be some electrons chilled on the outside as part of nitrogen. Okay, so this is what we're looking at for primary, secondary, and tertiary. And it's asking you for the primary, secondary, and tertiary labels for this new stuff. So N-methylpiperidine, look at it. You notice there is indeed a carbon here and a carbon here, along with the one that we discussed. So this one is going to be a tertiary amine. And here as well, we know this is going to be a carbon. That's what a benzene ring is. It's always carbons. And this is going to be a carbon here, and this is going to be a carbon there. So this is also a tertiary amine. So both of these are tertiary. But for extra note, if you wanted to go back to the original piperidine and aniline, you notice here, carbon here, hydrogen. So this is actually a secondary amine. And aniline, carbon here, but 2 hydrogens. This is a primary amine. Okay, so that's what we have there. So let's see now what we get for the answer. I think my picture is nicer. Just kidding. But as you see here, we have N-methylpiperidine, just a little stick sticking out. That indicates for methyl. And N-dimethyl-aniline, you have that benzene ring, and then you have the N, and then just 2 sticks sticking out. That signifies the 2 CH3s bond to it. And they both say that they are tertiary, so all this is correct. So finding whether they're primary, secondary, and tertiary is relatively easy, because we have to just count how many they're bonded with. But the important part is drawing them. You need to know the nomenclature, and you need to know how each one gives you a clue on how to fill in the rest of the picture. Okay, so with that, let's go to the next question. And let's see here. That's very strange. Sorry about that. Okay, give me a quick, let me just fill in and get back to where we were. Okay, this is correct as we discussed. Solve for, as we discussed earlier, we want to make sure that we solved for the oxidation number first. Correct. Okay, and then I guess this is just a free review, I guess, as we're going through. This is wrong because it is not a strong acid. It is a weak acid. Use ice table. Okay. And for this question here, we discussed that this is correct, although there's ways to go about it, but just go with PV equals nRT if you're always unsure. And now, let's see here. This is the one that we just say that knowing your names as well helps, because the one that says carboxylic acid is probably most acidic, but just knowing which oxygen can actually give away hydrogen, that's usually how it works. And then we discussed already in terms of ionic compounds. And on the question we were at, we were discussing the amines. So there we are, we're back to where we were, and this is also correct. There we go. And now we're going to go on to the next question. Oh, well then, I guess that's it for today, because it seems like that's all the questions that it's allowing us to solve for today. So with that, thank you again for watching this stream. Just get out of here. So thanks again, and as I said earlier, if you have any more questions, just follow the link in the description below. We'll be here solving many more questions, and hopefully we'll be able to answer any other extra questions you have. All right, thanks for watching, and my name is Fejiro.